Here we're going to look at the EM algorithm in a life testing setting. That's where we're looking at failure times with some of our data right censored. And this is probably the last example I'll do in the EM algorithm. Here we're going to let X be our failure time, and it's going to be exponential, where the times are greater than or equal to 0. The joint density would be this. Now, for the EM algorithm, we have to separate this into what's observable and what's not observable. And if we assume that the last N2 observations are not observable, we're not sorting the data, just whatever they are, we're going to put the observations that are censored at the end. So the first N1 observations, we observe their failure times, and then the last N2 observations, we do not observe their failure times. They're censored, so we know it's at least this value. And so first N1's observed, second the N2 failure times are unobserved, they're censored, and they add to N, our total sample size. Now here is the log likelihood, which is this, and I keep our observed data and our unobserved data separate. Now we take the partial, or the derivative with respect to lambda, and we get this. So minus n 1 over lambda, that lambda squared, and then that is just the same. Then we set this equal to 0, and solve, and we get this. Now this is the maximum likelihood estimate. So now let's look at the EM algorithm. So here in the E step, we need to find this Q function, which is the expected log likelihood, and it's in regards to our missing, the expectation is regards to our missing data given our knowledge, our observed data, our knowledge that the missing data is at least greater than the censoring time, and our initial estimate of our parameter. So everything's a constant except for this, our missing data, so the expectation comes in there. Well, it turns out that this is what's called a truncated normal distribution, truncated exponential distribution. And I do a video on that, and I'll put a link in the description here, and you can show that the density is this, where we're restricting it to x greater than ci, can be shown to be this, and the expected value is ci plus lambda. And now remember, in the E step, that we have our initial guess of our parameter, which is what this is, which is what is in here, which is what this is. So this is our first guess. Now we replace this piece here, and then we maximize this. So we take the first derivative and set it equal to 0, and we just showed that the first derivative equals, we get this, but this can be simplified is we're adding the first n, and then we can add the first, the next n2, we can put those together and just add them up, add our data up, and then we're adding into more of our initial guess of our parameter, and then divide by n, and that is our M step. Then we take this value, we put it back in the E step, recalculate, and get another lambda, and we keep doing this process until the lambdas converge. Now I'm going to give a quick illustration in R, but I learned very quickly that in R they don't use this parameterization. They don't use the 1 over lambda. They just say lambda times e to the minus lambda x. So what that does, it changes this m step that and this expected value. It's ci plus 1 over lambda here, and then since we're estimating we need a new estimate of our lambda, it ends up being n divided by this. It's the reciprocal. Everything is the reciprocal, and that'll make more sense when we do our R illustration. So okay, we're in R. We're going to look at life testing using the EM algorithm. First we want to create some data to simulate and illustrate. So here's the censor rate. I want about 10% censor rate. So I put that in sense rate. L1 is the lambda parameter for the original data, for the failure data, and then L2 is going to be the lambda for the censoring component, the censoring mechanism. Anyway, and then this little trick right here where you take L2 is L1 times sense rate divided by 1 times 1 minus sense rate. That generates the appropriate amount of sensing, and that's the theoretical rate. So sometimes a little more, sometimes it's a little less. And there's not a nice simple video explaining why that works, so that's probably going to be my next video. So let's have a sample size of 150. And here is our data. So the X is the failure rate of all our observations, all 150, and then there's a censor rate mechanism that will store those in C, and we want to know the minimum of those, and that is Y. And this is what Y is typically what we see in the real world. And I want to create some censoring variables and event variables. If the event is or if the censoring time is less than the failure time, the event is censored. Although if the event time is less than or equal to the censoring time, then it's an event. And then N2 is just a number that we censored. And here's our initial estimate for our parameter for the EM algorithm. And then here, this is the E and the M step combined. So this piece here, this line, it takes our given data and then adds a little bit more, and this is from the truncated exponential. That's our new estimate for our lambda parameter, and then we store that back in the original, and then it repeats just until we get convergence, but I just do it for 100 iterations. And then I want to look at the proportion of censoring out of curiosity, and this is the true lambda that we're trying to estimate. And then this is the maximum likelihood if we observed all of our X data, all of our failure times. This is the maximum likelihood in the censoring, so the sort of the standard survival maximum likelihood estimate. And then this is the EM algorithm estimate. So let's run this and see what we get. So here we had about 15% censoring. We're trying to estimate a lambda of 0.5. Our maximum likelihood estimate of observing all the failure times was 0.45, and this is the maximum likelihood estimate in the standard survival setting, and then this is the EM algorithm. And these two will always equal, kind of a neat little feature there. So let's run it again. 100 sample size 150. Here it's, the true MLE, the MLE under censoring, and this is the EM algorithm, and they're just dead on the money. Here we're about 12% censoring, and that is pretty cool. But now I want to plot this just to see how well it fits the data. So here, this is a plot of the Kaplan-Meier curve, and this is non-parametric, so it doesn't assume a parametric form, but like we did, we assumed it's exponential. So now let's plot it, and we'll just run it all. So here the black line was the Kaplan-Meier, which we said, and the EM algorithm is the green. You can't really see it here, and then the red is a true exponential, and then the MLE for censoring. And so the red is we generated, we plugged in a lambda of 0.5, and so we plotted that exponential. That's what the true exponential is. And then the MLE is if we observed all the failure times. And since the EM algorithm estimate is always equal to the MLE using the survival theory, they're always equal. I just plotted 1. So let's rerun that again. I want to rerun it all, and we'll see what we get. And again, it's just right on top of each other. So the exponential distribution is the correct. The Kaplan-Meier estimates it pretty close. And let's see what we got here. So it's always pretty close. And actually, no matter what our starting value is, it is always really, it converges to the same thing. So anyway, so that's the EM algorithm. Hope you enjoyed it. Probably my last video as an example to using the EM algorithm. I'm going to move on. I think I'm going to do this censor rate, how to generate a known censor or proportion of censored observations and still be it be random and independent of failure time. Anyway, hope you enjoyed it. Please like it and subscribe so you don't miss the next one. Bye.